All right, hello everybody. This is the second recorded lecture about diffusion. So we'll kind of pick up where the last recording left off. So last time we derived the various Fick's laws of diffusion, and I will summarize them here. So we've got Fick's first law, which talks about how particles move from regions of high concentration to low concentration under random walk conditions, so under diffusive motion. So you have some concentration of particles, and there we consider a flux of particles. So the Fick's law is written in terms of the flux, J, which for us, I'm going to use number units, meaning that the flux is denoted as the number of particles moving through a certain area per unit area times the time. So per unit area per unit time. And the direction, you can think of it as the direction sort of perpendicular to the area. So if you have an area, some kind of area here, then the flux sort of describes the motion of particles in the direction perpendicular to the area, because we're essentially counting all the particles that move through um, a certain area per unit time. And Fick's first law tells us how that works. It says that um, the flux of particles just moves down concentration gradients. So particles always move from high to low concentration. And the way to express that is in terms of the gradient, which is a sort of three-dimensional version of a slope. And just says that the diffusive flux is minus the diffusion coefficient times the gradient of a concentration, where the concentration here, the units of it are just the number of particles per unit volume. Now, in the book, it's a little different. These things have slightly different units instead of numbers of particles. The book uses mass, but it's sort of the same thing. You just replace number of particles with mass in kilograms. And then you get the same results. Okay, so second law I just sort of threw out there, but let's derive it. I think it's since we have time in the recording to go over this, it makes sense to derive it. So let's derive the second law. And by the way, in 1D, so this is the general 3D version. In 1D, if you just have a flux along one direction in space, then you don't need a vector really because it's just either positive flux, meaning in the plus x direction, or negative flux in the minus x direction. And it just like this, you just take a derivative of the concentration. I will say partial. Partial derivative means you hold all the other variables constant. When you do that differentiation, variables like the time variable in particular, and like other possibilities, like the other spatial variables, like y and x, it's assuming those are remain constant. So that's the 1D version. We'll apply it to some examples later. But I want to derive the second law, which is actually a combination of the first law plus the conservation of particle number or mass. It's because in diffusion, particles are neither created nor destroyed. You don't have any reactions, so the total number has to be conserved. So the way we set that up um, is we just count the number of particles that are in a certain region. So let's see here. So let's set up a coordinate system. Got your usual X, Y, Z. So you have your Z-axis, say, your Y, and your X. And let's imagine a box of particles, um, just like a cube or a rectangular, a cuboid box, where the height of it is going to be some small delta Z. Can think of them as like lattice spacings or something, but um, well, actually, this description is for sort of more macroscopic process. Diffusion works on many lattice spacings, so these are small distances that are small, but maybe not so small that it's just like one lattice spacing. But anyway, so you have some width dy, some x delta x, or dz, and some depth of the box that's delta x. So you have a box like that, right? It's a little cube. So it has a certain volume. That's just the product of the different dimensions, just the three different dimensions. And what we're going to consider is the concentration of particles inside the box. So what happens uh, to the concentration of particles in here? And so I guess this is the sense in which we are going to assume that the box is small. We're going to assume it's small enough so that this concentration is constant inside the box. So we're going to assume that inside the box there's some constant concentration that depends on the sort of location that we're at. We're going to assume that we sort of start at some location in space. Here I drew it as sort of the origin, but it could be an arbitrary location. So we're just going to say maybe there's some other, you can imagine some other coordinate system where this is like the origin, and then we're looking at what happens to the concentration that's some away at some position vector like that. So, okay, so, and we're imagining what happens to this concentration after one, say, small time step, delta t. We're going to try to figure out how does the concentration change in time. So we know that, first of all, there must be, in general, some initial concentration in there. So the concentration after a certain amount of time, delta t, should be the concentration at the initial time. And now we have to count all of the particles that come in and out of the box. Now, how do the particles come in and out of the box? They must leave through these surfaces. So through the surfaces of the cube. Because again, since particles can't be created or destroyed, the only way that particles can go in or out of the box is if they weave through these surfaces. There's 6 surfaces. It's just the 6 surfaces of the cube. And those are the only way in which particles can come in and out. Because the ones that are in the cube, that stay in the cube, since particles are neither created nor destroyed, they'll just stay there. They won't go anywhere. So we have to count all the different ways the particles come in and out. So first of all, let's do the particles coming in and out of the of the surface here at, say, um, along the x direction. So sort of back and front of the cube. Maybe I'll color it green or something. So the back face and the front face. Well, that should be related to the flux. So first of all, the area of the green surfaces here is just delta z times delta y. That's the area. And so we take that area, delta z, delta y, and we look at the flux through that area. So we have to take the flux, J, the diffusive flux, and dot it into the x hat direction. This is going to give us the number of particles, right, going um, well, we have to be careful here. So we need the particles going into the box. So if we're looking at the flux along the positive x direction, we actually, the ones that are going along the positive x direction and going into the box are the ones in this back surface. So the back surface is this J, and we should actually um, be a little careful and specify where we're evaluating this J. Show you why in a moment, but okay, we're evaluating this J at just the back wall there, X, Y, and Z. So we're gonna assume this origin point, the point at the origin is not 0, 0, 0, but X, Y, Z. So let me just denote that just so, because we want to make it general, right? We don't want to just study things that live at the origin of our system. We want arbitrary location X, Y, Z. So that's that back point right there, the one in the back. So, okay, if we evaluate the flux there, then and we dot it into the x hat direction, that would represent all the particles that are on that back wall that are going into the box. So going into the box from the x direction, right? And then since we need a concentration, we have to divide by the volume. So let me just denote this delta V or something. So I'm going to do this is delta V. And there's one more thing we have to do. Remember that the flux is per unit time. So we also need to multiply by the time. So this is number of particles per unit area and time. So we have to be careful about that. So we multiplied by the area already. And we just need to multiply by the time. And so this total quantity here, this will give us the total number of particles. Um, or net, rather, particles that are coming in. Okay, now what about this front wall? Um, right here, the one out in front. That one, if we're going along the positive x direction, those would be, if and the flux is positive, right, then those would be particles that come out. So the ones that are coming out must be subtracting from the concentration. And we still have delta T, delta Z, delta Y. But this time it's J, and we have to take the one that's evaluated at this front wall. So that's a distance delta X away from the origin along the x-axis. So there's a shift. We still dot it into x hat, so that part's the same. And we divide by delta V. So if I were to redraw the box, just so we can see which faces we're talking about the front and back faces. Let me just make it nice like that. So we have now taken into account the particles coming in from the back, and they could be coming out from the back too. It doesn't matter. It's just the way we've chosen to calculate the flux. We've dotted it into the x hat direction, which is towards positive x. So that means if you're looking at the flux towards positive x, then you have particles coming in from this back surface, and from this front surface, you have particles coming out. Or if you get a negative sign for that flux, of course, that would mean the opposite. But that's just the convention we're choosing because this is sort of the x hat direction. Hopefully that makes sense. Okay, let's do the next one. Next one is we will do it in some other color, like, I don't know, orange. Let's do the y hat direction. That's these sides, the left and right sides. So there we have plus. So we have along y hat, this back wall would represent particles coming in along the positive y direction. So we have again delta t. Now the area of the orange side is delta x times delta z. It's delta t, delta x, delta z. And then we have j evaluated at x, y, z. It's that back wall dotted into y hat all over delta v, the volume, because it's concentration, and j is number of particles per unit area per unit time. So altogether up here, this is again number of particles. We need to divide by the volume to get the concentration. And then similarly, subtract the particles coming out of that front wall. Same area, delta x, delta z, and j, but now it's the particles at that front wall, so it's y plus delta y z dotted into y hat, and then that's all over the volume. Okay, so if again I were to draw a little square for that, the surfaces that we're talking about here are the left and right surfaces. So here's our little box, and we're looking at the particles coming in from this front surface and this back, or this left, the left surface and the right surface. And the particles here are coming in from here and out from here. That's what we mean by positive flux at those surfaces. So, okay. Finally, hopefully you're seeing the pattern here. We just left with the top and bottom surfaces. I guess I'll make them this darkish blue or something. That's this top and bottom surface. So again, and draw a little schematic. This is our box. Then the surfaces I'm talking about are this top and this bottom. And again, our convention is that so here, this was the y hat direction. Now z hat is in this direction. So that means the particles are coming out of the top and they're coming in from the bottom. That's the convention for positive flux. So, okay, we have delta t, delta y, delta x this time because the area of these top guys are, delta y, delta x. And you have j, x, y, z, this time dotted into z hat, the z direction, all over the volume. And we subtract delta t, delta y, delta x. And then we look at that top surface at z plus delta z dotted into z hat. That's the particles coming out from the top. Okay, that's it. And now we'd have to do a Taylor series. We have to expand these fluxes around x, y, z. So we don't want to have this z plus delta z stuff. We just want to expand each of these around the central value that's at XYZ, the center, the corner of the cube. So that's should be simple enough, right? What do we get here? We get C of R at t plus delta t. I'm going to subtract the CRT over here on the other side, and now I'm going to approximate. So the first thing to notice is that I can, if I multiply and divide the top and bottom of this term by delta x, the first term, then I'll get the volumes canceling. So I can actually write this as delta t over, or the in the volume element cancels the x the y and z parts upstairs. So we're just left with delta t upstairs and delta x from the volume element downstairs. So you have j dotted into x hat minus, and up here it's similar delta t over delta x. And now we do a Taylor series. So that's pretty simple. We have j evaluated at x, y, z, dotted into x hat. Then the first term after that is the first derivative term. So it's plus, and it's going to be x minus x. It's x plus delta x minus x. Again, if you haven't seen Taylor series, it's okay, but we're just approximating this function around the coordinate around delta x is equal to 0. So the first, and maybe, so the first correction, maybe that's a better way to think about it. So the first correction is proportional to delta x, because that's how far out we go. It's like we have the slope times the distance we go. So the distance we go out away from x is just delta x. And then the slope of the function is just the derivative along that direction. So it's delta j, delta x, and then you dot it into x hat. It doesn't matter that it's a vector function. You're allowed to do Taylor series for a vector. It's it's allowed. And we don't need any higher order terms for that, actually. So we'll see some nice simplifications happen. You can already see that this term will cancel that one, hopefully, because they're the same. All right, so here we're left with delta t. Now the delta x and delta z cancels from the volume element, and you're just left with delta y on the bottom. And we have j dot y. And then you have similarly delta t, delta y. And it's the first term is j dot y. And then it's plus delta y. And then the derivative of j with respect to y dotted into y hat. Okay. And finally, you have delta t over delta z, j dot z minus delta t, delta z, j dot z hat plus delta z, dj, dz dotted into z hat. All right. So that is all the terms. And now there's a lot of cancellations. There's this term cancels that one. This one cancels that one. This one cancels that one. And we're left with a pretty simple expression. So first of all, well, okay, we'll get to it. So we're left with C, the concentration at some location at a little time later minus the initial concentration is equal to minus, and we'll see what happens here. These delta x's actually cancel when we multiply it out. So we're actually just left with delta t, and we're just left with dj dx knotted into x hat. And we have plus, or sorry, minus delta t dj dy dotted into y hat minus delta t dj dz dotted into z hat. We can divide both sides by delta t. To cancel all these delta t's, which is kind of nice. So those all cancel. And on this left-hand side, you see you have the difference between the concentration divided by the time interval, which we're looking. This is just another expression. If we send the time interval to 0, this is just another expression for a derivative. So this actually, on the left-hand side for small time intervals, or you can think of it as doing another Taylor series. But for small time intervals, this is just the derivative of C of R of t with respect to the time variable. And again, we have to use partials everywhere because this is a function that depends on both space and time. So we have to keep all the other variables fixed. All right, and on the other side, we have this interesting construction where it's like the derivative of the function dotted into with respect to a variable x dotted into like the direction along that variable. And there's an overall minus sign. So let me write it out, I guess. It's dj dx dotted into x hat minus dj dy dotted into y hat minus dj dz dotted into z hat. This actually has a special notation in 3D like this. It's actually minus what's called the gradient operator dotted into J. And you can think of the gradient operator as just applying the derivatives along each direction, and then the vector is given in terms of those directions. So you apply a derivative along x and dot the result into the sort of x direction. And this is like a vector which you can, dot into other vectors basically. Okay, so it's just a notation like that. Makes things a little bit compact. And this is Fick's second law, sort of. If so at this point, it's just what's called a continuity equation. And it describes conservation of particles. It's true for any kind of flux. It doesn't have to be a diffusive flux. This is just expresses the fact that particles are neither created nor destroyed. So the only way they move in and out of a box is via a flux. So this is just a consequence of particle conservation. It's called the conservation equation, or it's like a continuity equation. That's what it's called. Just says, hey, look, if particles are neither created nor destroyed, then the only way the concentration ever changes inside a box is via a flux of particles through the box surface. That's all it is, pretty simple. So it's just particle conservation. And if we combine it with Fick's first law, then we say that the only way particles move is via random walks. So we just replace this J with the diffusive J. And then you're left with minus, and this is called a divergence when you dot this gradient thing. And so it's the divergence of the diffusive flux, but the diffusive flux was minus the diffusion coefficient, and it's the gradient of the concentration. The minus signs cancel, and you get this really nice expression that it's just the divergence of the diffusion coefficient times the gradient of the concentration. And if D does not depend on space, if it's just a constant, so for constant D, you just get that the D can come out and you just are left with the divergence of the gradients. This has another special name, which is called the Laplacian. It's like a second derivative. Um, if I wrote it out in terms of coordinates, it's just all of the second derivatives added together. And that's Fick's second law. Okay, so that's the 3D version. In in 1D, you would have just a single variation of the concentration along one direction. So you just have that. Okay, so how do you actually use these things? Well, we need some examples. So one way is to use the first law, which just tells you about the flux. You can use it to estimate steady state fluxes if you want. Um, that's one thing you can do. So let me just go back here to Fick's first law, right? It's the slope of the concentration times the diffusion coefficient is equal to the flux. So if the slope of a concentration is constant, then you have a constant flux. So a typical example, so let's do like example of the first law. Usually you have some kind of steady state situation. So imagine we have a plate of iron like this. You have like a iron plate. And imagine we're trying to embed carbon into this plate to make steel. So the way we might do it is on the left, we have a carbon-rich concentration of carbon. And then we allow this carbon-rich environment to saturate the iron with carbon atoms by allowing a flux to go through the iron plate into a carbon poor environment. So this will set up a situation where you have some concentration on the left, say 1.2 kilograms per meter cubed. That could be the concentration of carbon on the left. And I'm going to use the book units where it's mass per volume. And on the right, you could have a smaller concentration, say 0.8 kilograms per meter cubed. In which case, if you wait a while and you have these concentrations be fixed, then what happens is that you set up a steady state flux of carbon going between the two environments. You have a high concentration here, that's C on the left. It'll decay and go to the lower concentration on the right. And in the middle, it'll be a linear function. Now, why is it linear? You can actually figure out why, because in the steady state, things no longer evolve in time. So this thing right here, Fick's second law, at steady state, it's equal to 0. And what a second derivative is just a derivative of the first derivative. So that means that the derivative of the concentration is equal to zero, which just means if something has a zero derivative, that means it's constant. That means that the first derivative is a constant. So that's what happens in the steady state. You have that the first derivative of the concentration is a constant, meaning the slope is constant. And so you have a constant flux. So J is constant. So let's figure out what this J is. So J is negative diffusion coefficient times dc dx, which is the slope. So for us, so we need to specify, we need some more numbers. We need like the thickness of the plate. Let's say it's the thickness is 5 millimeters. And we need something else. We need the diffusion coefficient of carbon inside the iron. So the diffusion coefficient of carbon inside the inside the iron is 3 times 10 to the minus 11 meters squared per second. And so what we have is everything we need to compute the flux. Let's just see what it is. So the flux is minus the diffusion coefficient, 3 times 10 to the minus 11 meters squared per second. And now the derivative, the first derivative is just the slope. It's the change in concentration. So the change in concentration across the iron plate, the final concentration is sort of CR. So it's CR minus CL. That'll actually give us a negative sign because we know that the flux is in the positive direction, right? But this is the difference. You're going down in concentration. So the concentration difference is oh, in here. Okay, so the concentration difference is negative. And then um, we need the, of course, that's the change in concentration over the distance, which is just the thickness of the material. This is 5 millimeters. So, okay, let's plug in numbers. This is going to be 3 times 10 to the minus 11 meters squared per second times, so it's 0.8 minus 1.2, but I'm just going to cancel the minus signs. It'll just be 1.2 minus 0.8, and that's kilograms per meter cubed. And that's all over. Now you have to convert the millimeters to meters at 0.005 meters. And what we get is, well, we need to plug into a calculator. Let me just do that real quick. So I have 3 times 1.2 minus 0.8 divided by 0.005. So it's 240 times 10 to the minus 11. Upstairs, we have the units of kilograms. Uh, there's some cancellations. So like this meters squared cancels two of those guys. So you're just left with over meters there. But there's another meters here. So the overall effect is you have over meters squared, and there's also seconds. So meters squared seconds. And this makes sense, right? Because the flux should be in amount of particles, which in this case is kilograms per area per second. So that's what you get. Written another way, it's 2.4 times 10 to the minus 11 kilograms per meter squared second. So that's a typical flux. It's not very much, and that's because you don't need that much carbon actually to get into iron to make a nice steel, and or usually for these interstitial solid solutions, you do have just a small amount of the small molecule which is then well described by diffusion. If you have a lot of the particle, then diffusion starts to make less sense because the carbons will run into each other and stuff, which is not taken into account in diffusion. Okay, so that's basically an application of the second law. The first law, the Fick's first law, it's for steady state problems. So it's used for steady state for the most part, where you have like a constant flux and you're trying to figure out what the flux is based on the differences in concentration. Okay, what about the second law? The second law, let me go back to this other color. So the second law, that one, you look for specific solutions. So, sorry, I'm using shorthand. Let me just rewrite the law again. It's the derivative with respect to time of the concentration is equal to diffusion constant, and then it's two derivatives with respect um, to space. So we already saw one solution that describes how concentration spreads over time, right? We assume here we have some initial spike of concentration, at the center of our coordinate system. Imagine some initial like giant spike of concentration, and then we just watch it evolve over time, right? It spreads, right, and becomes more and more spread out over time, and we just watch this process. And we know the specific solution to that, right? We sort of talked about that um, by analogy with the random walk. If we like start a bunch of random walkers at the center at x equals 0, and we ask what's the probability of observing it somewhere later on, that's the same as putting a bunch of concentration at the origin and asking how the concentration spreads out. The solution is as a function of time, well, it's however much initial concentration you put there at the beginning. And then it's this Gaussian, this bell curve. There's 4 pi fusion coefficient times the time, and then there's an exponential of minus x squared over 4 dt. That describes the spreading out process from the origin. So spreading out process. Uh, That's usually not exactly the kinds of problems you have in material science because you usually don't like put a bunch of concentration in just one spot. What you usually do is you apply some treatment to a material, and you want to know how long it takes for that treatment to penetrate your material. So say you have like a chunk of material, some material, and you apply a very high concentration of something to one side of it. So you like apply some treatment. Maybe it could be a second atom you want to imbue the material with to make like a nice alloy. And what you want to know is how does the concentration of that treated material penetrate into the material over time? It'll start like just near the surface, right? And over time, it'll spread into the material. And usually you're treating it just like on one side of the material, like on some surface. And so you're asking, how does this treatment spread into the material over time? So this is increasing time. So to do that, you need a special kind of solution where you fix the concentration at a certain level. So say this is your X and this is your 0, this is your concentration. You need a solution where you fix the concentration to some value at like at the origin. So this is some fixed C, I don't know what to call it, C um, treatment or like some high value of C. It's just some high value. And then far away, you also assume that the concentration goes to some fixed value, might be some low value like C0. Actually, let's use the things in the book. I think this is called CS. This value is CS, and then far away as x goes out to infinity, you assume that you go to some other concentration C0. Now that could be like zero, so it could be there's no treatment deep inside the material. But in general, you might have some residual amount of treatment just already in the material, so then you need that. And so then the question is, how do these things evolve? If you start off with just a very sharp kind of concentration profile, how does it change over time to become more and more smoothed out, right? And how does it penetrate into it should basically more of the concentration on the left should penetrate into the material. So this should be, again, increasing time. Now, I'm probably going to do an example of this in class, but what I did want to do is actually show you a way of solving this equation because I think it's kind of cool. And it makes use of the fact that um, we know that the basic feature of random walks is that the distances, like the average distance that you go away from where you started, grows like the square root of time. So there's like a fundamental variable on which things depend, which is this diffusive variable, which I'm going to call z. And it's the position that we're at divided by the square root of 2 times the diffusion coefficient times the time. If like you have two different diffusion processes that have the same value of z, then it sort of is the location at which both of the diffusive processes have distributed the same amount of concentration. It's basically a way of rescaling your positions and your times so that it takes into account this idea that the distances that random walkers move, that they grow like the square root of the diffusion coefficient times the time. I know that might not mean much, but I think we do some more examples in class it'll make a little more sense. But I just wanted to show you by doing this redefinition to this new um, coordinate, if you want, the z, you can actually solve the equation. Because this is general, this second law equation is very hard to solve because it's got time and space in it. And, that's tricky. It's like two different variables. You have derivatives in both. Okay, so let's see what happens. Let's imagine we just look for concentrations that just depend on this combination square root of x over square root of 2 dt. Let's imagine all our solutions are like that. So assume all solutions just depend on this combination. So just on this combination. Okay, so what would you get? Then the derivative with respect to the time t, that would become um, a derivative with respect to z times the derivative of z with respect to t. And this is something called chain rule. It's the way you can go from one variable to another. If you haven't seen that, that's okay, but that is how you just would convert a derivative with respect to time to one with respect to this new variable. So, okay, we have dc dz, and then the derivative of this z with respect to t, you do need to know how to do derivatives of like square roots and stuff, but it will be, let's see, minus 1/2, and then it's x over square root of 2d, and it's t to the 3/2. And what this is actually we can rewrite this part as minus 1/2. This x over square root of 2d, we can absorb one of the square root of times, and we just actually get z divided by t. So we'll see that that'll actually help us once we combine everything. So let's do the derivative of c, the second derivative of c with respect to x. So we'll do one derivative at a time. For the first one, we have dc d z dz dx. All right. If we substitute in, so this is the c dz. Now dz dx, x is only out here, so actually this is just 1 over square root of 2 dt. Okay, and then we have to do the same procedure again. This derivative of x, this is a constant because it doesn't depend on x, so it just comes out. Square root of 2 dt. And then we have the second derivative of c with respect to z times dz dx. It's just the chain rule again. Again, if you haven't seen it, don't worry about it. But if you have seen it, I think this is a nice application of the chain rule. Is to solve the diffusion equation. It's pretty nice example of how you can simplify a very complex equation. So dz dx, that's just again this you just the derivative just gets rid of this x, so you're just left with again another factor of 1 over square root of 2 dt. So in the end, you have 1 over 2 dt times the second derivative with respect to z squared. All right, let's put it together. So we have dc dt is now becomes minus 1 over 2t times z times dc dz. And on the other side, we have d times 1 over 2 dt, and it's two derivatives with respect to z. And the miracle here is that the t's cancel on both sides. So in the diffusion equation becomes a single equation just in terms of z. So the t's cancel on both sides, and these d's cancel, and the 2's cancel. And you're left with this kind of amazing result that the entire diffusion equation just reduces to minus z dc dz is equal to d, the second derivative with respect to z. So that's crazy. It's just a simple now ordinary differential equation, meaning it's an equation, it's with derivatives, but just with one variable in it. And we can rearrange things a little bit. So let's me just write it now as regular derivatives because it just depends on one variable. Now this is still tricky to solve, but we do one more substitution. So we let w equal to the first derivative of c with respect to z. We can do that just redefining the concentration. We're now not looking at concentration, but its first derivative. And then we have that this becomes the second derivative is just one derivative on w. So this becomes dw dz is equal to minus zw. Now this equation we can solve because we can sort of separate the w and the z. This is the physicist's way of solving things, normally not allowed in math class, but you can group all the w's on one side and all the z's on the other side. And then you just integrate both sides. The integral of 1 over w is the log, the natural log of w, plus an integration constant. And that's all equal to minus the integral of z is z squared over 2. And then there's also an integration constant. And now we can get rid of the log by exponentiating both sides. So we take the exponential of natural log of w plus a constant is equal to the exponential of minus z squared over 2. You see it's an exponential of z squared. That it should remember what z is. Z is x over square root of 2 dt. That's just your Gaussian. We've actually derived the solution to this differential equation is has a Gaussian in it. Okay, so exponential of a constant is just a multiplicative constant. I'm going to call that, I don't know, I'm going to call it 1 over W0, actually. Exponential of a log just gives us the function back. So W of z is equal to this exponential minus z squared over 2. And now what we're left with is that WZ, my computer is lagging a bit. Okay, so WZ is equal to some constant W0 times exponential of minus z squared over 2. Now, the last thing to do to get the full solution is recognize that this W was dc dz. That was the first derivative of the concentration. So whenever you have a differential equation, like an equation with derivatives, if you have two derivatives in it, like this original equation, this actually always, when you solve this, it'll have two arbitrary constants in it, like that are set by initial conditions and things like that, or boundary conditions. So it's two derivatives that always have two constants. We found one of the constants that was like the constant of integration here. That's this one, that's sort of constant 1. But there will be one more constant of integration when we integrate this last equation. So we again can integrate both sides. So let me rewrite the equation. It's dc dz is equal to some constant we don't know times the exponential of minus z squared over 2. Last step is you integrate both sides with respect to z. Uh, the integral of a derivative is just you get back the function itself. And we're going to be a little careful, I guess, with the limits. We're going to integrate away from 0. So I guess I need a dummy variable for this variable of integration, but here we have 0 to z. I'm going to make this z bar for like just the variable of integration. Okay, so this just gives us back the function. And then we're left with, gives us back the function plus a constant of integration. So plus some constant. I'm actually going to define it with a minus sign. Minus C0. This is a constant of integration. That's equal to the integral from 0 to z. W exponential of minus z bar squared over 2 times dz bar. Now this integral actually has a special name. what this is, it's if you imagine what this thing in here is just a Gaussian function. So if we plot like as a function of z bar, this exponential of minus z bar squared over 2, it just looks like a the bell curve. And we're looking at it away from 0, so it just looks like a bell curve like that. This is 0. And what this function is, it's the area under this curve up to a certain value z. This is the area under the curve. It has a special name. It's something called the error function. So if you take a Gaussian and you look at the area under the Gaussian up to a certain value on one side, you get something called the error function. I can actually show you that. Let me pull up the relevant screen here. I can just show you that integration and like on some computer software. Here we go. Let's do integrate exponential of minus, say, z bar squared over 2, where z bar ranges from 0 to z. And you see it's this, there's a factor in front of this, that's pi over 2 thing, but that's okay because we already have a constant there, so we can absorb that into the arbitrary constant. But this function is the error function of z over root 2. So in the end, this thing, the solution is CZ is equal to W0, some constant, and maybe I'll call it some other name now that we've absorbed the square root of pi over 2 in it. I'm just going to call it some constant A. It's a constant to be determined by like your boundary conditions. And this is going to be an error function, error function. And it's z over square root of 2, but I'm going to actually, well, okay, a couple more steps. Z over square root of 2, and then there's another constant, this constant of integration out here. I'm just going to put it on the other side and just call it plus b, some other constant. Now let's substitute in for z. And we get our final result. Our general function is a function of x and t. There's two arbitrary constants which we can use to specify boundary conditions. We can use it to sort of specify that we want, for instance, the concentration to be a certain value at x is equal to 0, say. We'll be able to do that with this with these integration constants. Just have a error function, and then we're going to substitute in for z. Z, remember, is x over square root of 2 dt. So once we plug that in, that's going to be x divided by square root of 4 dt. There's that 4 again. And then plus a constant b. That's the general solution to our diffusion problem. And we're going to actually be able to use this to answer questions about like how fast treatments spread into materials. So I think I'll leave that for class, but this is the general solution. To, again, our equation, which was, one derivative of time is equal to, two derivatives, d times two derivatives of position. And this is called Fick's second law. It's also called the diffusion equation. And this is a general solution, but of course it is constrained. It's constrained. It assumed that the kind of solution we're looking for is just a combination of space and time, of x and time, that's of this form. So it's a special kind of solution, but we'll see that it allows us to solve situations like this where you have like a fixed concentration somewhere. Um, by the way, this is called this process of like guessing a variable that combines the space and time and getting an equation, reducing the equation of two variables into one, just an equation with one. That's called a similarity solution. All this is called a similarity, similarity solution. Okay, so I think that's it for now. I guess I will do an example of the usage of this error function in class.